Hello, everyone. This is Scott, your instructor, best friend, and pretzel maker. If you guys came to my house right now, I'd give you a pretzel, but alas, you're not. Too bad for you guys. Next year, just let me know. I'll give you guys pretzels. Today, we're going to get into one of my favorite topics of all of CS1 and CS2 and data structures, sorting. I just like sorting a lot. It gives a nice order to everything, and it just seems so intuitive. So we're going to cover just a brief introduction into the higher concepts, similar to how we had this introduction into why we cared about containers. We'll do this intro into sorting and the different things we're going to be looking for, the different things we're keeping our eyes out for. Then I'm going to do a quick intro. It's not quick. I'm going to go into selection sort and bubble sort, which are the first kind of two naive ways to do sorting. It turns out they're also both the worst, but that's okay. We'll get into that. So first, what is sorted, right? I know this seems maybe rudimentary and maybe seems kind of too basic, but let's think about this for a sec. Why sorting? Why do we want sorted data? Well, sorted things are going to be some sequence that is in some specific order. And we've been talking throughout the semester about the importance or not importance of order, right? Our priority queues and our heaps, they're going to have things in order, and our binary search trees are going to have things in order. But our basic vector, our basic list, none of those things have a specific order, but they might have order. A queue and a stack certainly have order, but they're not necessarily an ascending or descending order. They're just the order that they were placed in. And so the thing we're thinking about when we're talking about sorting is, how do we go from entropy? How do we go from randomness or not order to some order? So, right, basic things 1, 2, 3, 4, 5, 6, 7. That's an easy order. Numerical ordering, we're very good at. We're very used to. Certainly, string-based ordering or character-based ordering, A, B, C, D, right? That's very intuitive. But when we get into objects, we start getting into more interesting orderings, and we get into orderings that can change. So, in the example of like the MCU, we have Iron Man, then we had the Incredible Hulk, then we had Iron Man 2, then Thor, then Captain America, then the Avengers, right? The order there matters. The order isn't arbitrary, and the order is also specific. In this case, it's telling a narrative. We could argue that we could change that order to be like, movie time frame, where Captain America starts first and then gets into Incredible Hulk and then Iron Man and Thor, right? But the idea here is that this is at least the release date, right? The dates that they were released by the movie studio. So there's lots of things that we can get into ordering, but what ends up not really mattering is the algorithm. And that's what we're going to be studying this next week and a half, is the algorithms to get us into an order. Now, why? Right? Like, why are we even doing this sorting? Why not just process our data as is? We can figure out how to process it alternatively than having to spend all this time and energy thinking about sorting and writing the sorting. So why? Well, there's a lot of reasons, but I just want to hit on this kind of rudimentary example first. So it turns out that us humans, we are really good at pattern recognition. We're good at pattern matching. We're good at kind of seeing how things fit together. And we're actually a lot better at it than we currently are with a computer, right? Like, computers can do some pattern matching and some recognition, but they can't intuitively know certain things. Whereas we are pretty quick at figuring out things and pretty quick at processing data. But this is important. We're not that good. So I have two different examples to show you what I mean by we're both good and we're not good. So there's this idea called subitizing or subitzing. I don't know how you want to pronounce it. Subitizing, which is the idea that we have a pretty advanced optical connection to our processing center in our brain, that we can very quickly recognize groups of items. And so I'm going to flash some shapes on the screen really quick, and then I'm going to pull it away and then ask you a question. I'm going to be asking you questions about how many of each kind of shape there are. So just as a heads up, that's what I'm doing. But I'm only going to flash it up on the screen for a short amount of time. So take in as much information as you can. Okay, here we go. All right, I know that was quick. I know it was fast. But let's see if you did okay. How many red stars were there? How many blue circles? How many green squares? If you want, you can write this down. You can pause the video, write it down, see if you're going to be right. So the red stars, there were 3 of them. Blue circles, there were 4, and green squares, there was only 1. Now, I went really quick, right? But even there, flipping back, you could easily verify what you were looking for, right? So think about this for a sec. Before I flipped to the screen, I didn't even tell you what kinds of shapes there were, let alone the number of shapes, let alone how big the shapes were going to be, right? I simply just told you there would be shapes and you need to have some information about them. We flip to here, you can easily see, oh, there's a grouping of 3 objects. Each of those 3 objects, there's 1, 3, and 4. We're really good at picking up that kind of information. And it turns out we're good for a lot of reasons for doing this. And we use it all the time, that we can count small number of items without really needing to count them, right? I'm using air quotes when I say count. We can just automatically recognize the number and we automatically internalize, again, in our central processing, how many of those things there are. Okay. What about that one? I know I kind of sprung that on you. Let's do it again really quick. I want to know how many stars, circles, and squares. All right. Let's actually break this down. Let's make it even more easy. Which of the shapes had the most objects? Right? Was it stars had the most, circles had the most, squares had the most? Now, I'm actually going to show you a sorted output instead, right? I showed you before an unsorted output, but I'm going to show you a sorted output really quick. And I wanted to ask you the same questions of which one of these has the most objects, and then how many of each of them. All right, that's a little bit easier, right? I showed you a certain presentation that's very different than the presentation I showed you first. And so you might be able to make a guess. It's actually pretty hard because you can't guarantee that the shapes are all the same size, but you can take a guess that red had the most, which you'd be right. Now, I would be amazed if you could actually get these correct numbers. I had to actually sit there and count on my screen. There's 39 red stars, there's 23 blue circles, and 38 green squares. Now, if you don't believe me, let's go back for a sec, right? These are the sorted elements, and you actually see that the red and the green are very similar. And if we go back to the original image, the fact that these are both different sizes amongst each other and that they're in irregular patterns make it really hard for us to automatically visualize what's going on. And even now, some of you might be in your head verifying those numbers I showed you and trying to count up all of these shapes. And it's still really hard even when I'm talking, right? But if we flip back to here, again, I didn't show you for very long and you still could figure out that there were 4 circles, 3 red stars, and 1 green square, right? So the whole point here is that we as humans process information differently. And it turns out that we have an upper limit on the number of things that can be involved before our brain shuts down and stops automatically recognizing and instead moves into a analytical processing of actually going, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, right? There's actually a shift that happens there. And it's different for each of us, but it's around 4 to 7. Anything more than 7, and it gets complicated. Anything less than 4, though, most people can just automatically pick up. So the whole point here is that the sort is moving us towards an ability for us as humans to automatically recognize patterns. And it turns out that this is just like a very kind of niche area of data visualization. That we as humans can only really look at small amounts of data at any given time. And so with visualization, with sorting, we can start to mold that data in a way that we can notice patterns, in a way that we can notice differences. Let's say, for example, right, contextually, we're talking about COVID-19 cases. Instead of showing you a graph, right, where I have a visual representation of the number of cases, instead I just list out for you timestamps with numbers, and I just list those out. Sure, some people can really quick on like an order of magnitude see growth, but it's also a lot harder to see the growth, especially as like an exponential curve, as opposed to if you just look at that data in a graph. The same way that if I give you individual data points, let's say I just started listing off numbers, it's also really hard to contextualize that information because once we get past 4 or 5 numbers, our brain starts to forget all of the relations that we formed, and we start just listening to individual pairs instead of larger collections. Now, this is a generalization. Some of you might think differently, right? This is just kind of a large level idea of why do we care about data visualization. So it turns out that again, this is niche. This isn't the only reason for sorting. This is just a human data visualization problem of sorting. So it turns out that algorithms also need sorting. So when we consider like an anagram, right? If we want to find out if something is an anagram, the easiest way to do that is to sort each string and then check individual characters. If we want to remove duplicates, the easiest way to do that, again, sort both collections and then iterate through those collections to see if there are duplicates. If we want to do a mode or a median calculation, that's going to be based on a sorted collection, right? So in your head, you've been doing sorting throughout your computer science career. Now that you have all of these tools in your tool belt from the perspective of how do we think about complexity, how do we think about algorithms in a more templated way, now that we have all of those ideas, now we can start getting deeper into, okay, how can we actually understand these algorithms at a more finessed and minute level? So again, just as a high level kind of conversation moving into these sorts, all of these things are templated. And what I mean by that is really all we care about is some kind of comparison between two objects. This could be a simple less than greater than kind of operation, or it could be a compare function pointer, which is more how the algorithm sorts work in the STL library. We're not going to get that deep into it. We're just going to talk about templatized and well overloaded operators for our sorting. But sorting algorithms, they don't care about types. All of our conversations throughout this week, as you've probably gotten used to with our container conversations, are about the algorithm, not about the type. Now, efficiency here comes down to actually two different things. One is going to be the number of data comparisons. Now this, I say thing in kind of single quotes here. What I mean by that is like the thing we're doing when we're sorting is we need to compare different objects. So if we can make our number of comparisons small, then that means we can sort faster, right? If I can take 10 items and sort them in order in, let's say, 15 operations, comparison operations, that's much better than if I have to do 100 comparison operations, right? A compare is the processing unit. So we want to reduce that as much as possible. The other efficiency we're getting into is the data movements. Remember that the moving data takes time. And so the more we have to move data, the more time is going to be incurred by making those movements, those swaps. Now, we can give this whole side conversation around, well, we could just have sorting pointers and we can just be moving pointers, which reduces the amount of data movement. But still, at the end of the day, if we can move, n log n pointers, that's still better than moving n squared pointers. So we still care about data movements. All right, the other thing to point out here at a high level before we start getting into all of these different sorts is that we are going to assume that all sorts are going to be in place. So that means they don't get any extra memory to do their operation. And that you'll see when you do your own programming, your own sorting algorithms for the programming assignment, that gets a little tricky, that gets a little complicated. That might not be as efficient as it could be. But to make things fair, to make things even, we're going to make everything in place, which means that everything has to be done within the memory that was allocated in the original container. So we don't get any extra scratch space. And again, I just want to hit on this idea that the two things we're really going to be talking about is going to be the efficiency of the comparisons and the efficiency of the movements, because it turns out different sorts have different comparisons. All right, so we can roughly sort the canonical, kind of the classic sorting algorithms into two different bins. One of them is going to be in quadratic form, and what I mean by quadratic is essentially like n squared. And we're going to see as we get into selection, bubble, insertion, and shell, as we get into those sorts, we'll see that we're talking about n squared kind of operations. Then the other one is going to be more advanced, and most of these advanced sorting algorithms are going to fall into an n log n domain, and that's going to be obviously much better than our n squared space. So we're going to go over all of these throughout the week. Today, I'm going to cover selection sort and bubble sort is kind of the most, the algorithms for them are most straightforward. And so that'll give us a good kind of baseline understanding of what we're doing before we get into the more complicated algorithms that are going to be more in those advanced sorts. Okay, cool. So selection sort. This is the most basic. This is pretty straightforward. The basic idea here is that if you want to fill your array from smallest to largest, the first thing you do is you select or you find the smallest item and then pull it out of that array and put it in your new array. And you just keep going, right? Find the smallest item, remove it, okay? In the remaining things, find the next smallest item, remove it, find the next smallest thing, remove it, keep going, right? Rinse and repeat. So let's run through a quick example. We have this starting array. Again, remember we're talking about templatized things, so even though this is numbers, it works the same regardless of what kind of type you're storing. So the very first step we need to do is we need to find the smallest number in our array. To do that, we're essentially going to have to check every single element. So the first check, we say, is 15 the smallest element so far? And the answer is yeah, so we record 15. Great, got it. We then check the next thing, right? Is 15 greater than less than 2? Well, it turns out 2 is smaller than 15. So now we're going to record 2 as our smallest number. And I'm going to keep track down here at the bottom of the number of comparisons we're making. Because remember, one of the efficiencies we're going to measure is the number of comparison operations. The other efficiency is going to be the number of swaps we have. So far we only have one comparison. We then need to compare 2 and 20. 2 is still smallest. 2 is still smallest. 2 is still smallest. You see a pattern emerging. Smallest, smallest. Great. At this point, we have exhausted our collection. We know that 2 is in fact the smallest. So now we need to swap the first location with our smallest object. So in this case, we'll swap 15 and 2, right? That just promotes 15 over one space. 2 gets stored at the front. Now I've grayed out 2 because we know that this is the correct location for 2. There isn't any other number that is going to go before 2 because we've already determined that 2 is the smallest number. So we keep going. This is our second iteration. The first time we check, 15 is the smallest. We check against 20, still smallest. Great. We flip with the 12. 12 is still smaller than 14. 6 is smaller than 12. 6 is smaller than 9. Great. At this point, we're going to swap the 16 and the 15. Okay, so you see the pattern that's emerging. I'm going to go through these pretty quick. We look for the smallest thing within the 20, the 20, the 12, the 14, the 15, the 9. And again, because we're totally great at detecting patterns, we can see that the 9 is the smallest, but let's keep going, right? That 12 is going to be the smallest, great. 9 is going to be smallest. We need to flip with 20, great, and we keep going. It turns out that every step of the way, we're going to be getting one smaller comparison. So this last check, we have to make 3 comparisons. We then need 2 comparisons. We then need 1 comparison. I think that's off. That should all be -1. That should be 0. That should be 1. That should be 2. It doesn't really matter for our calculations. All right. So then eventually we get to the point where we don't need to make any more comparisons because we're done. All right. So, the reason we're saying 1 is because, yeah, okay, I know why we're saying this. We're basically saying, is this compared to itself? Yeah, you could say that these should all be -1, but that's just a kind of an edge case in how we're doing this computation. It turns out that it doesn't matter. We'll see in a sec. All right, so we see that this n-1 per iteration comparison, but how many swaps did we make, right? Because remember that one of the metrics we're looking for is the comparisons. That's going to be these comparisons on the side. Then the other metric we're looking for is how many swaps did we make. Now for this first iteration, all we really did was swap the 15 and the 2. The second iteration, we just swapped the 6 and the 15. This one, we just flipped the 19 and the 20. Then the 12 stayed in place. It actually didn't need to swap. The 14 didn't need to it didn't need to swap. 15 didn't need to swap, 20 didn't need to swap. But in theory, it did. In terms of our algorithm, it's going to swap. We just don't know that yet. So what we're going to say is that this is going to take 1 swap per iteration. So essentially n times. So we're going to have 6 swaps. So let's look at the algorithm in pseudocode. The basic idea here is that our first line of code, or our first thing we're doing, is we're essentially looking at every single element in the array. For each element in the array, which really is more like for each position in the output array, we are going to try to find the smallest object. For all of the items from that place and up, We're going to do a comparison to then capture the smallest item. And then lastly, we're going to swap the position we are trying to fill within the smallest item that we found. And that's what I mean by like, we're actually always going to swap. We just haven't really shown that. So technically this is going to be like item 4 is swapping with item 4. It's just our algorithm doesn't care about that yet. Right, so again, this is the basic idea behind selection sort is for every element in our array, we're going to find the smallest unsorted item and then swap it with the current the current position. That's the basic idea. So again, when we're talking about comparisons, we're talking about an n-1, n-2, n-3, n-, right? We're getting into this very, very discrete structures level sequence or series. If you recall your discrete, this is going to be n squared over 2 plus n. And back to our conversation at the very beginning of the year around order of operations, what we really care about is our exponential growth here in the n squared. Even though it's being divided by 2, we don't really care about that. And this single n growth is far outshadowed by the n squared growth. So we're going to say that this is on squared. Okay, now this intuitively makes sense. We have to do n comparisons, right? We have to set n numbers, and then each number is essentially going to be comparing n number of times. So that's where we get that n squared. Even though it's kind of it's a decreasing n, we're still going to call it n for comparison's sake. The growth is still on track for n squared as opposed to a linear growth. Okay, that's nice. Now, what about swaps? Right? It turns out that every single line, right, every single number we assign, the 2, the 6, the 9, the 12, each of these are only one swap. Oh, that shouldn't be n squared. That should just be n. Ignore that right there. That should just be n. Right? That's nice. If we have really large objects, that's probably best to only, we are doing essentially the best that we can do. We only move each object one time, which is nice. That's good. That's solid work. Okay, now this is an important question for sorting algorithms because it turns out that some sorting algorithms, it matters a lot. In some sorting algorithms, it doesn't matter at all. So for our example, does the input order matter? So what I mean by that is, if we run our selection sort on an already in order array, does it perform any different? If we do it out of order, right? This is the exact opposite of in order. Does it have any different results? So it turns out that for selection sort, there's no difference, right? And if you don't believe me, go ahead and go through these by hand and you'll see that it doesn't matter. In both of these, we're essentially going to be finding what goes in this first place, and then we iterate through the entire array looking for the smallest thing. Both of these first steps are going to identify the 2, and both of these first steps are going to swap the 2 with the first location. Now, you might be seeing a pattern here that in this case, we could modify our algorithm to detect if we need to do a swap or not. And in this case, we wouldn't need to do the swap, but we would still step forward and now find the smallest item, which we would again identify as the 6 and then not swap. So we're still looking at on squared comparisons, and we can fiddle with this on swaps. If we're smart, we can check that on swap. All right. So yes, you can modify to swap or not swap if you don't need to, but you're always going to have to make n squared comparisons. All right. That's selection sort. Again, pretty straightforward. If you don't remember anything from this portion, right, when you get to exam 4, what you need to remember is selection sort is you select the smallest item, put that in order. That's it, right? That's all we're doing when we're talking about selection sort. Select the item, put it in place. All right, cool. Let's move on. Let's get into bubble sort. Bubble sort is notoriously terrible. We'll get into why it's notoriously terrible. There's a great clip of Obama when he was running for his second term. He was being interviewed by some tech space, and he was asked, what does he know about technology? And he said, well, I don't know much, but I know the bubble sort's the worst, right? And it's a funny joke because it transcended into politics. Anyway, it doesn't matter. Bubble sort, let's get into it. The basic idea here, again, is that it's very simple. The algorithm is very simple, and it seems intuitive at the start, but we'll see why it's so terrible. The basic idea here is that you're just going to compare neighbors. You're going to compare index I with index I plus 1. If those two things are out of order, then flip them, right? Swap the neighbors. And what this leads to is an emergent behavior that as you keep comparing and as you keep switching, the large numbers will bubble up through your array and your smaller numbers will bubble down through your array. So, right, let's go through an example really quick. We've got the same ordered list of numbers that we had for our insertion sort, or our selection sort. So now we want to go through and do our bubble sort. So the very first thing we do, we say, hey, is 15 and 2 in order? Now again, I'm going to be keeping track of the comparisons and the swaps down here in the bottom corner. So first thing, are these two things in order? That's one comparison. Well, they're not, so we need to swap them. That's one. Great. Then we step forward one. Are these in order? That's one comparison. They are in order. Good. We don't need to swap anything. Next up, we go to these. Are these in order? Nope. So we need to swap them. Great. Check. Are these in order? No. Swap. Are these in order? Nope. Swap. Are these in order? Nope. Swap. Now notice that as we flip through here, really what we're doing is we're just pushing the 20 through our array, and eventually we get to 20 being the top, and now that's kind of in the correct location. Now, 2 being at the front is actually entirely coincidental. That's not guaranteed to be the right position for 2. But what we do know is that at this step, our 20 is done. And I'm going to show you a modification. This isn't actually real bubble sort. This is a modification to bubble sort, but I'm still going to show you it. We can essentially say 20 is in place, right? We can essentially not check that last position anymore. We know that the largest object filters up to the top. Now, I'm going to keep going through the algorithm as it is written, which is that it will keep checking no matter what, but for visualization purposes, the 20 is in the correct spot. So we start over. We go back to the beginning. We go to 2 and 15. Are they in the right order? Yes. 15 and 12. No. 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 Great. 15 found its spot. Okay, we keep going. I'm going to run through these examples. They're pretty boring to watch, right? And notice that every time we're essentially bubbling up the largest item. Now, at this point, we technically don't need to keep going, right? We didn't make any swaps when we checked from this 2 to this 20. So when we do that, we can technically say, hey, we're good. We're in order. We don't need to keep checking. So the algorithm is going to detect when the sorting is done and when you can just stop. Now, when we talk about best case and worst case, think about that. If your array is already sorted, then your bubble sort is going to be OC. Well, it's not OC. It's going to be ON. ON comparisons. It's just going to check every single element once. Worst case scenario is it's the reverse order, and then it takes absolutely n squared times. Not even like approaching n squared. It takes n squared operations. All right, so let's look at the algorithm. The algorithm here is extremely straightforward. You're just going to keep looping until this exchange flag is set true. And in your loop, you're going to set the flag to be false. And then for every single pair in the array, so that's like 0 and 1, 1 and 2, 2 and 3, right? I and I plus 1. You're going to look to see if they're out of order. If they are, you're going to swap them. And you're going to set your exchange flag to be true. So you're essentially keeping track of, did I do a swap or did I not do a swap? And so you're going to keep doing this loop, this do while loop, until you're able to make it through the entire array without needing to do a swap. Again, pretty straightforward, pretty simple, not complicated from an algorithm standpoint, but now let's look at the complexity, right? Our first pass, n-1 comparisons. Second pass, n-1 comparisons. Last pass, turns out, n-1 comparisons. Now I have this asterisk here because you can modify the algorithm to not go all the way through your array. You can stop it to only go like I through I minus the number that you've assigned. The algorithm doesn't do that for a lot of reasons. It turns out there's a more efficient way to do a bubble sort. I'm saying more efficient. It's kind of tongue in cheek because it's still also terrible, but it's still faster than what we just went through. So it turns out that in this case, right, every single pass we do, we have to do n-1 comparisons. That's leading us towards, you got it, an n squared kind of operation. That's not great. Now, what about swaps? Right? Swaps, our worst case is going to be out of order, and that means we're going to have to swap everything n-1, then n-2, then n-3 down to 1. And we already determined from our insertion sort, that's going to be like an n squared divided by 2 plus n kind of situation, which is n squared. Again, that's worst case complexity for our bubble sort. Now, again, here, this is really important for a lot of sorts, but for bubble sort in particular, the input condition drastically changes the efficiency of this algorithm. So if our input best case scenario is in order, we're looking at n-1 comparisons, that's an ON operation, in 0 swaps. We don't have to change the position at all if we are already in order. So when we're looking at this, we're looking at, is 2 need to swap with 6? No. Does 6 need to swap with 9? No. Does 9 need to swap with 12? No. 12, 14? No. 14, 15? No. 15, 20? No. We've just gone through the entire array and our exchange flag is still false. We then exit out of our loop and we say, hey, it's sorted. We're good. That's as efficient as you can possibly be, right? You can't actually go any faster than that. Now, it turns out, though, that our worst case is real bad. If it is in reverse order, we will do n squared operations. Not just like approximately n squared, we're going to do n squared operations. And it turns out we're going to do n squared swaps as well. That one's not as exact because it turns out that very close to the end, you're only moving one thing. But comparison-wise, it's going to be real bad. All right, now I actually am going to give you guys a homework assignment that will show that there is a modification to bubble sort where instead of going from 0 to n, the next pass you go from n to 0. So you both bubble up and then you bubble down, and then you bubble up and bubble down and bubble up and bubble down. And it turns out that every time you iterate through in both directions, you can make your sort slightly better. It's not that much better. It's still an O n squared sort, but it's slightly better. Okay. So hopefully this whole conversation has gotten you in the mood for sorting. These are the two most basic sorts. Again, they also turn out to be two of the most terrible sorts. We're going to get into more advanced, more efficient sorts on Wednesday and Friday. Now, your homework is the best thing ever, and I'm going to post this link to the Discord channel, so you don't have to copy this down. I'll also post it to Blackboard. There is this fantastic video from 1981 called "Sorting Out Sorting." I had to watch it when I was in college. It's something that still brings me joy. All the things about it. And they go through and they graphically represent the different sorts that we're going to be talking about. And they go through and they show you with some pretty good animations what those sorts look like. And so I'm going to have you guys over the course of the week watch all of it. But for right now, just watch the first about 9-ish minutes. If you want to watch the full thing, go for it. But the first 8 minutes are going to prep you for what we're going to talk about today and Wednesday. So go watch that. You got to answer me 2 questions, your favorite part and your favorite sort so far. The rest of the week is going to be all the rest of the sorts. That's what we're going to be talking about. We're going to be checking off that list, going through the quadratic sorts and then into the advanced sorts. All right, cool. Go ahead and bring any questions you guys have to Monday and we'll talk about it. We'll get into some of the details if you have questions. Either Monday or Tuesday, I'll be posting the last programming assignment, which will be, you guessed it, doing sorts. It'll be not too bad. You're essentially going to implement a number of sorting algorithms and then compare them to each other. See if you can suss out these best and worst case scenarios. Yeah, cool. All right, there we go. We'll get back into it on Wednesday. Have fun. We'll talk to you later.